Hey, hello everyone. I'm Rahul Jadhav. I'm here to speak about intent-driven security automation. Now, you might have heard about intent-driven automation a lot of times in last couple of days. What we are trying to do is, in the context of security, how you can use some of these concepts of intent-driven automation and how we can simplify security is what we are trying to achieve here. Now, there is one of the things that I'm going to discuss about is a project called as Nimbus. Now, this project is an NSF-sponsored project. Dr. Tom Rondo just mentioned about a project called as SCRAN. This project is part of it. So it's an open source project, part of the NSF umbrella. So, telco deployments are changing. Already, we have seen that some of the Kubernetes orchestrated workloads or containerized orchestrated workloads moving into telco deployments. It's a norm these days. It provides you a great level of abstraction. It provides you a great level of disaggregation. But the primary risks, there are two risks, right? Like you add in all these abstractions. You have container runtime. You have network runtime. You have storage. You have all of these layers upon layers. This provides you immense flexibility. But the primary problem that one faces, there are two primary issues that anyone will face in the context. One is with respect to performance, and the second is with respect to security. So that's basically, and handling security at different layers is especially problematic. What I'm going to talk about is what is the architectural mindset that we can bring in to handle security at all these layers. One more important point is that in the context of some of these networks are going to be made use of in the critical infrastructure. So it becomes immensely important to have security baked into this solution rather than giving it as an afterthought. You look at so this is a CNCF security and compliance landscape. What it shows is basically all the toolings that is currently used in the context of, these are all CNCF tooling. All of these, or most of these, are point solutions. You can secure network, you can secure service meshes, you can secure systems, you can do secure containers, all of these aspects. The primary problem that I'm going to talk about is, all of these point solutions bring in complexity, the deployment complexity. Eventually, you have to take care of security as a whole, and how would you deal with that? That's the primary theme of this talk. The other part that I would like to talk about is how the threat model itself is changing. As compared to any traditional threat model in the context of any telco deployment, you had appliance-based security you work with. You do SCTP init flooding attack protection, you do DDoS protection. All of these were fine in the context of earlier threat models in the context of existing traditional telco deployments. But the threat model is drastically changing when it comes to ORAN-based deployments. In fact, not necessarily ORAN-based, even the 5G core is going tremendous change. So how do you, some of the information that is mentioned here, these are excerpts from actual ORAN threat modeling guide, which is produced by ORAN Working Group 11. As you can see, some of the points, some of the attack vectors that I mentioned relates to supply chain attacks, relates to container escape attacks, relates to a bunch of other things that we had never previously envisaged in the context of telco deployments, because those were considered to be a closed source. Attacks still existed, attack vectors still existed back then, but because of the disaggregation, now you have your CUs, DUs moving into data centers, moving into public clouds even. And how would you secure all of those things is the primary aspect that this threat models bring in. Now, a general approach that is taken today in most cases in the context of security and a few other cases is that you have something to secure. You bring in, you identify a policy engine. You want networks L3, L4 to be secured. What are the set of network policies that you can bring in? Then you have these network policies in the context of specific engines. For example, in the Kubernetes world, you have CNIs, and the CNIs operate at their own level. You have network policies, fundamental network policies, and on top of it, you have Cilium network policy, Calico network policy, which brings in their own different ways of handling this network security. The point is, today, most of us are actually deploying point solutions, where you bring in network policies, you try to secure the network first, do the network segmentation, then you bring in service mesh, you bring in systems hardening, you bring in pod security context, pod security policies, and things like that. So the primary problem with this is twofold. Eventually, if you make a change from one engine to another, you have to deal with all the complexity of moving not only the engine, but the associated policies and rules to this new engine. The second part is, how do you do defense in depth? A lot of this security intents could be fulfilled at multiple layers. You want to make sure that you can attach a security policy at each of these layers. So by using a point solution, essentially what we are doing is, we are saying we'll secure from the network perspective, then we'll look at the system's perspective. So this is the phased-wise approach that is taken, which makes it extremely difficult to do defense in depth. The third aspect is handling dynamic workloads. The way in which workloads are deployed, we were talking about deploying hundreds of thousands of edge clusters, extremely dynamic workloads. Having a static security policies is not going to help. How do you make sure that what the workloads are doing at runtime, and based on that, if you can identify what the security posture is and cater to those needs, is what the world is evolving towards, and that is something that would be needed in the context of such kind of deployments. Now, well, are we the first to actually think about this in the first place? There have been discussions before. One of the primary things that have happened before is standardizations of the policies itself, policy formats itself. Like you have network policy, right? Network policy is a resource which is mostly satisfied by most of the existing container network interfaces, CNIs. The challenge there is, in most cases, the innovations is actually outpacing the standardization. So what happens is, you see Cilium network policy, Calico network policy superseding the standardized network policy. So we are not able to keep in pace, the standardization is not able to keep in pace with innovation, and this is not a new story, this has been a story since ever. The same happened with service mesh interface, SMI service mesh interface. Yeah, there was a standardization effort which is not so much in active progress right now. The primary reason is that the standardization was way too slow. The actual service mesh engines were innovating at a much faster pace. So it becomes irrelevant at some point in time. Now, what is it that we are trying to achieve? Like I said before, security is a hard topic. Already the Kubernetes itself is hard. Security on top of it is like comatose, right? Like it's extremely difficult given the multiple runtimes available, multiple layers available there. One of the things that we are trying to do here is we are replicating the success of storage design in the context of security. What storage did was, again, storage is an extremely complex subject. You have multiple types of devices, you have character devices, block devices, you have so many SLAs that have to be satisfied. What they did was essentially had a way to actually specify an intent in the form of a persistent volume claim that gets attached at runtime. Depending upon what storage devices it has, it checks what kind of interfaces are present, what kind of SLAs can be satisfied, and then attaches itself, the persistent volume claim attaches itself to a persistent volume dynamically. Now this is achieved through certain Kubernetes patterns, and that patterns are something that we're going to make use of in the context of security solutions as well. So that's where we are moving towards. So the primary point is, can we make use of Kubernetes reconciliation logic even in the context of security intent? First, as a user, can I specify a security intent at a high level? Again, not a new topic. You've heard Nephio folks talking about security, intent-driven automation in the first place. This is in the same veins, but in the context of security. What we are saying here is that, can I specify a security intent at a high level? And there exists a Kubernetes reconciliation logic which checks what kind of engines are available under the hood in that particular deployment, identifies the right set of rules and policies, and then deploys it. So the reconciliation logic here engages with the security engines and decides what policies has to be used. Now, if there is a dynamicism, like a lot of times you can say a security intent could be, if my workload is exposed to public internet, I would like to have certain set of policies to be in place or certain set of security intents to be in place. This kind of dynamic policy setting is now possible, which was not even thinkable before. Either you have to first identify which of your workloads could have public access. In the context of this dynamic, hundreds of thousands of clusters getting deployed on a regular basis, you cannot manually identify what are the workloads going to be doing, and then try to identify a set of policies and rules. So this is where the Kubernetes reconciliation logics comes into play. Now, Nimbus is a project that I'm going to talk about. It's an open source project. It's part of the SCRAN effort, Security Enhanced Radio Access Network effort. Dr. Tom Rondo talked about us in his keynote today. How do you add a zero trust architecture to your whole solution? How do you have defense in depth for whatever deployments you're going to do? How do you specify security intents at a high level? And as you can see in the first column here, you have security intents, a high-level security intents. Then you have security domain. These high-level intents could be then instantiated either using network policies, service mesh policies, admission controller policies, systems policies, port security context. It could be anything. Security intent is different. The instantiation is different. And then that instantiation can then be handled by individual policy engines, the security engines. It could be Cilium, KubeArmor, Calico, Multus, it could be many other, Kyverno, and all the Kubernetes native. So what we are essentially doing is the security and compliance landscape of CNCF goes in here. This becomes the heuristics which is automated through this particular project. And then you have security artifacts, policies, rules. Now, no one is manually creating these policies and rules and handling alerts and telemetries manually. That's what the eventual goal is. And under the hood, the whole point about making use of the right security primitive in the right context, whether to make use of eBPF, whether to make use of seccomp or SELinux, is all driven by this policy engine. So what we are saying is that you specify security intent, and then using those intents, we can automate everything henceforth. Now, once you have security intents, the logical next step is to group them together so that you can have a blueprint and you can deploy blueprint. For example, if it's an ORAN deployment, you can identify, for ORAN, these are the set of policies that would make sense. These are the set of security intents that would make sense. You do the same thing for enterprise, cloud security, IoT, edge deployments, and you identify basically blueprints. Again, nothing new here. What we are doing here is very specific work in the context of security automation. The notion of identifying a set of intents, creating a blueprint out of it, almost everyone. You heard Google talking about TNA on day one, doing the same thing. It's a generic architecture. Leveraging it in the context of security is what we are trying to do here. So you have set of blueprints. These are essentially vertical specific bundles of intents. And then intents are high-level security requirements. Those are, and I'll talk about what are the characteristics of an intent, because you need to have a definition of intent. If you don't have that definition of intent, what will happen is eventually the users will codify the actual policies and rules into intents, at which point those intents will become engine specific and you'll lose the advantage of that abstraction. So there has to be some best practices, some checklists as to what those intents should contain, should not contain. So I'll talk about that in a little bit more detail. So you see, all of this work is in public. 5GSec is the GitHub organization, and you'll see the architecture and all the documents, including the source code in there. Now, this is the detailed architecture for Nimbus. Like I said before, the whole automation is orchestrated by a Kubernetes operator. Basically, the two things as a user that you pass in. A, the security intents, and where those security intents are applicable. What are the resources? You specify those resources using selector labels, namespaces, or you can say, I want this intents to be applicable on X apps. And then these are the set of intents, and the intent binding are X apps. So it will go identify those intent bindings and then apply the corresponding policies and identify the corresponding policies and rules in the context of that particular deployment, which involves identifying which all engines are deployed. Another important aspect that we realized that we would need in the context is, and this gets often very less talked about, is once you have an intent, you deploy an intent, and how do you get that feedback loop? I think that's a big gap there today in general. Like, you deploy an intent, do you know whether the intent is satisfied or not? Do you know whether an intent is fully satisfied or partially satisfied, or you need to know this information. And if an intent could not be satisfied, you need certain recommendations in the context. Especially in the context of security, you say that you want to not allow privilege escalation across anything. Then do you have the right engines in place to actually fulfill that intent? So this kind of feedback loop is also equally important. The advantage with Kubernetes operator is that it has visibility into the target Kubernetes cluster. It knows what is deployed in there. It can take actual actions. The other part is based on the alerts. Like one of the possible feature that we have envisaged as part of this framework is that you get an alert in the context of one particular engine. That alert can then trigger other actions. It could trigger other events that could then lead to a new policy altogether. So how do you identify? So all this dynamicism, it was not possible before with static policies and rules. This is what basically is changed with intent-driven security automation. So I need to explain some design rationally. Like I said before, intents are a high-level specifications, right? And those have to be agnostic of any policy engines. If you eventually codify the actual rules as intents, then it becomes specific to a policy engine, at which point you lose all the advantages of having a separate security intent. That's one important thing. There would be engine adapters who would say that I could satisfy this particular intent in this particular way. So there is some logic, some heuristics that is deployed, which says, for a network policy, there is an adapter which says, oh, I see this intent, I know how I can convert this intent into this particular rule, and then satisfy this intent. The advantage of Kubernetes is that we have all the cross-linking here, all the cross-references here. You have a security intent that is then eventually converted into policy. So, and that there is a mapping kept there. So you'll be able to see that this particular security intent is actually fully satisfied or partially satisfied and things like that. So there is an inherent advantage of making use of Kubernetes resource model in the context. The third is, and this is a very important aspect, where defense in depth comes into play, where you have the same intent satisfied by multiple engines. You say DNS manipulation, and that's one example that I usually like to quote. A DNS manipulation attack can be handled at multiple layers. It could be handled at the network layer, it could be handled at the systems layer. So basically this engine can say, oh, here's the intent, my systems adapter is saying, this is how I can protect it, my network's adapter is saying, this is how I can protect it. So you automatically get defense in depth approach. And the fourth part is the operator watches for external events and can fulfill intents based on it. So this is the dynamic aspect of fulfilling the intents itself. Lot of times your policies and rules might be tied to certain events that are happening at runtime. You might not want to just inject a policy or a rule statically. So you might want to deploy it in context to certain heuristics that a solution can see only at runtime. So this is another thing that would be allowed. Now there were certain design choices that we had in mind when we looked at this whole framework. Should we go with a Kubernetes admission controller? Because admission controller will look at the deployment and then can take a decision as to for protecting this you need certain things to be in place. Why is it that we went with the Kubernetes operator? The primary problem with admission controller is that once it is deployed, it does not have any visibility into it. It's an admission controller, right? You can mutate it, you can validate it at deployment time, but once it is deployed, once it is in the runtime phase, you do not have any visibility into what it is doing. So you need a Kubernetes operator model to actually have visibility into what the workloads are doing, and based on that, take some action. That was our primary reason to have active reconciliation, and that can be achieved only using a Kubernetes operator pattern. Like I said before, it's important to understand the mapping between the policies and intents. Like I said, it's very important to give that feedback to the user, saying that you have deployed the intent, but it's not satisfied. So you might have to take in certain additional actions to satisfy that intent. Next, I'll go into some examples, defense in depth. So I talked about preventing DNS manipulation here. So an intent is prevent DNS manipulation. There are multiple engines which can come into play here. So the corresponding adapters, and this adapters is where most of the heuristics are codified. These adapters know that, oh, this is the intent, so I can create a corresponding policy out of this. These are the adapters who provides defense in depth. So in this case, you see there's a kubearmor adapter. kubearmor is a CNCF project which does systems hardening. It does preemptive mitigation of the process execution, the file access, the network access, and things like that. So you can say, do not allow anyone to make any changes into resolve.conf. That's one way to actually do DNS manipulation attacks, or do not allow access to raw sockets itself. From the network policy perspective, from the Cilium adapter perspective, you can say allow DNS packets to specific endpoints only, so that you can't have DNS manipulation. All of these are extremely difficult for general security administrators to understand, unless and until we make their lives simpler by telling that these are the high-level blueprints that would make sense in the context of your environment. They're not going to be able to deal with the security issues in their environment. So this is a step in that direction. Same is in the context of software deployment tools. There are a lot of times the base images contains a bunch of binaries, packages which are never used. There are even application deployment tools, software deployment tools such as apt, APK, YUM, DNF. Most of the attackers leverage these tools to dynamically inject scanning softwares like Nmap or mass-scan, so that they can then after that they can do lateral movements. How do you prevent these? Again, this is an example where there are two engines coming together and saying that I can do this at my level, I can do this at my level. And that's how you fulfill the intent. There's another interesting use case. A lot of times certain workloads needs added hardware-based protection. Now, one of the intents that we have developed is, can you say, I want to deploy a particular 5G workload in HSM-enabled environments, such as something like enclaves. It could be Intel SGX, AMD SAV, any of these. So the Nimbus, the security intents itself says that some of these workloads needs to be deployed in a hardware-enabled security environment. So the intent is specified, the execution is then carried out as part of the adapters. The adapter will create a policy or a manifest which would allow that workload to be deployed in an enclave-based environment. This is a high-level security intent schema. Now, the reason why I've put in here is because there were certain things that we took into consideration while defining the schema. One of the important things was, what are the detection methods, mitigation methods, and all of these are already available. This is something not, this is the project which has not come up with all of this information. There already exists MITRE, tactics, techniques, and procedures. There exist NISA controls. There exist a bunch of other frameworks who give you that kind of information. All you have to do is understand that information, convert it into a schema, and have a way to dynamically convert those intents into the corresponding policies and rules using adapters. That's the primary aim of this project. Now, what are the challenges that we faced? The two challenges primarily that we faced. One was in the context of the intent bindings. How do you know which resources this intent should be deployed? It's not an easy task. Some of the policy engines support selector labels, some of them supports match expressions, and it is not mandated by the Kubernetes that a particular policy engine should be making use of certain specific primitives to identify the workload. Most of the policy engines use their own. Of course, the namespace selection is present, it's omnipresent, all the policy engines do that. Selector labels is a common pattern, but match expressions is not a common pattern. Some of the engines do it, some of the engines don't do it. The challenge that we faced is that now we are harmonizing this deployment of intents across all this, using all these policy engines. You have to specify a rule spec for those policy engines. How do you come up with the least, the common denomination across all these policy engines and work with that? That was one of the challenges that we faced. The second problem was the security intent feedback loop. whether the security intent was fulfilled or not. But then again, that problem was mostly fulfilled using, exists something called as owner reference in the context of Kubernetes environment. Using that, we are able to handle it. I have a quick demo here. I know we have, okay. I'm going to quickly run through the demo. What it shows is, again, this, like I said before, the source code is all available in open source. The aim of this demo is to show a security, what happened? Oh, okay. Yeah, so you see first it's showing that there are certain deployment policy engines that exist in that particular system, particular deployment, and then there is a security intents operator that is present. These are the set of security intents that are mentioned, the examples that I gave: prevent DNS manipulation, block access to service account token. Again, all of these things can be done at multiple layers. These are the different security intents that are present. Then this is the security intent binding, which says that these security intents should be applicable on this set of resources. That binding exists. Now you apply the security intent and the binding. What it does is, once you apply this, the security operator comes into play, the automation operator comes into play, and then it automatically identifies which are the policies that needs to be automatically created using the policy engines that are already deployed there. So, yeah. So what it's now showing is that a set of policies that are auto-discovered. So it says netpol. So all of these policies are auto-discovered policies that are dynamically generated. Yeah. So I'm going to, so what this demo shows is that a set of policies that are auto-created along with the rules, and after you enforce these rules are enforced, and then you get security. So if the attacker tries to do something malicious, then it is protected. That's the primary point of this demo. So what it's showing is that there is a telemetry event that you get if there is a violation here. So someone tried to execute APT, and that got denied. So there was a policy violation, and that's what was shown in the context. Now the immediate goals for Nimbus, we want to make use of this in the context of ORAN security, create blueprints. That's the primary aim here. Again, there are certain platforms that we have targeted. It's already deployed to some extent in the context of certain platforms. We are looking for more integrations. The certain adapters are already present there, as I've listed in there. Anyone who wants to know more, wants to get associated, would love to talk and take it forward. Thank you. Any questions?
So you mentioned that once the intent is created by the security admins, the operator will create the required policies.
Yeah.
So does it mean that a particular Kubernetes deployment need to have those individual entities deployed already?
Yeah, if it is not deployed, the intent will say come out that it is not fulfilled. Okay. If none of the, so for example, in the case of DNS manipulation attack, let's say for example, there does not exist any network, a CNI which can fulfill network policy, and there does not exist a system policies based on kubearmor, let's say for example. Then it will say that the security intent was applied, but it was not fulfilled, meaning that the references were 0. As simple as that.
Okay, and what if there is a proprietary engine that is under Nephio?
Yeah. No, it is possible that someone can write a proprietary engine because it is fully decoupled. Like you can have your own adapter at the end of the day, and you can keep, it's completely, the only thing that the adapter does is, given a security intent, what are the heuristics that you can, what are the actual policies and rules you can enter. So that particular adapter can be completely proprietary. It is possible, that model is possible. Currently we don't have any adapter which is proprietary, but in the future, someone might actually come up with a proprietary adapter, yes.
Okay, sorry, one last question before I. So once the policy
Yeah, we have both the models. That's a very interesting question, actually. Yeah, so yeah, in the context of security policy deployments, no one wants to auto deploy the policies. So one of the things that we had identified is that at this point, right, like you see the review/apply option for the Nimbus policy. So there is an optional review model. So the policy is applied, but it's still not, policy is identified but still not applied. So the CRD is created, but it's not activated. That model also exists. So that is one point that we have taken into consideration as well. Thank you. Thank you. Right on time. Thank you very much.